Alright, here's another example of using calculus to graph by hand a function. F of x is equal to x times e raised to the negative x power. Let's see if we can run through all of the things that we're supposed to here. So first thing we'll run through is going to be the domain. The domain for exponentials as well as polynomials would be all real numbers, so no domain issues with this one. For number 2, as far as intercepts are concerned, we'll start with the y-intercept. For the y-intercept, we set we set x equal to 0. Plug that in. That'll be 0 times e to the negative 0 power, which is 0 times 1 for 0. Lets us know that the y-intercept is going to be at 0, 0. The x-intercept, we set f of x equal to 0, and we solve for x. According to the zero factor property, that means that either x is equal to 0 or e to the negative x is equal to 0. Now, e to the negative x is considered an exponential decay function. Decay functions, and growth functions, I guess, for that matter, don't actually touch 0, so this has no solution. But the first one does have a solution, and that lets us know that the x-intercept will be the same as the y-intercept, and that'll be at 0, 0. Next up, third thing that we want to take a look at, actually, has just escaped me, so I'm going to recheck the book real quick. Yes, symmetry, of course. For purposes of symmetry, we are going to evaluate f of negative x. F of negative x is going to be equal to negative x times e raised to the negative x. Now, because that changes the e to the negative x into e to the x, that is why this is going to have no symmetry. This test changed it from an exponential decay function to an exponential growth function, and that's no bueno. For number 4, we look for the period, and this is not applicable to exponentials, so this only applies to trigonometric functions for the time being, so don't need to worry about that one. Next up, as far as asymptotes are concerned, there will be an asymptote that we need to check for on this one. That is because for an exponential decay function, especially when multiplied by a polynomial function, we need to consider the limit as x approaches positive infinity of x times e to the negative x. I realize that we're not technically allowed to plug in infinity, but if we were to allow x to go to infinity, the x would be going to infinity, and e to the negative x would be going to 0. As such, we have an indeterminate form. Now, it is an indeterminate product, so in order for us to use L'Hopital's rule, we will need to force a fraction on this. Since we already have a negative exponent here, it makes the most sense to refer to this as x divided by e to the x, to which we can then apply L'Hopital's rule for an indeterminate quotient. Once in this form, derivative of x is going to be 1, and the derivative of e to the x is e to the x. If we now allow x to go to infinity, your numerator will be 1, your denominator will be approaching infinity, meaning that this limit will be equal to 0. This lets me know that there is a horizontal asymptote at y equals 0, but only to the right. If we were to consider the limit as x approaches negative infinity, we would have negative infinity times positive infinity, and that would not be an indeterminate form. Rather, it just lets us know that as x gets really big in the negative direction, y will be getting really big in the negative direction as well. Next up, I think we're probably ready to do a little bit of calculus, so let's take a derivative and see if we can figure out those critical points. For this derivative, I am going to be making use of both the product rule as well as the chain rule. So we are once again differentiating x times e to the negative x power. Product rule says this will be the first times the derivative of the second. Derivative of e to the is e to the, but then the chain rule says multiply by the derivative of the exponent, plus the second times the derivative of the first. Derivative of x will simply be 1. Rewriting this using a little bit of algebra, this will be negative x e to the negative x plus e to the negative x. To get our critical numbers, we'll need to set this equal to 0. And because it's set equal to 0, factoring the left-hand side will be to our advantage. This only works because it's equal to 0, the concept of factoring. Applying the zero factor property tells us that either e to the negative x is equal to 0 or negative x plus 1 is equal to 0. The first one, for the same reason as before, has no solution. So the only critical value that we're going to get is going to be x is equal to 1. Once again, this one has no solution. So we wind up with only one critical value. That one critical value is going to break up our domain into two possible intervals of increase and decrease. So a critical value that we got was 1, giving us two intervals to test, and that will be from negative infinity to positive 1, and from 1 to positive infinity. To test these, I'd like to make use of x equals negative 2, and we'll use x equals 0 for the other one. Now we are plugging this into the first derivative that we got, and the first derivative that we got was f prime of x is equal to e to the negative x times negative x plus 1. So plugging in negative 2 to test the first interval, that'll be f prime of negative 2. That'll be e to the negative negative 2, so positive 2. And then negative negative 2. Oh, shoot. Yeah, that one's still okay. That one doesn't contain x equals 0, though. We'll have to use x equals 2 for that one. My goodness. Well, we're all flawed. It's okay. E to the positive 2 and then negative negative 2 plus 1. This is 3e squared. Important thing that we take out of this is that this is greater than 0, which lets us know that this interval right here is going to be an interval of increase. Then for the other value over here, x equals positive 2, we will use f prime of 2. That'll be e raised to the negative 2 power with a negative 2 plus 1 associated with it. Negative 2 plus 1 is negative 1, and e to the negative 2 would be over e squared. The important thing that we get out of that is that that is a negative number, letting us know that this interval is an interval of decrease. Now that allows us to use the first derivative test to classify our one critical point. We change from increasing to decreasing. That lets us know that x equals 1 is a local maximum. Now I am interested in turning this into a critical point, so what I'm going to do is head back to the original function. Original function was, as you see here, f of x equals x times e to the negative x power. I'm going to plug in 1 to that to get a y value. Y value that we get is 1 over e. So 1 comma 1 over e will be our local maximum. Next up, we're going to do this with concavity as well, see if we can determine what the concavity of this thing is. So we had that f prime of x is equal to e to the negative x times negative x plus 1. We're going to differentiate that. Second derivative will tell us inflection points and intervals of concavity. So this will be first times the derivative of the second. That'll give us a negative 1. Plus second times the derivative of the first. Once again, derivative of e to the is e to the, and the chain rule says multiply by the derivative of that exponent. Now, a little bit of distributive property and combining like terms should take place next. So this will be negative e to the negative x. I'm going to take this negative 1 and distribute it through here and distribute the e to the x as well. That'll be plus x e to the negative x and minus e to the negative x. Combining our like terms will give us x e to the negative x minus 2 e to the negative x. This simplifies, or rather factors, into x minus 2 times e to the negative x. Now once again, we're going to be setting this equal to 0 and solving for x. By the zero factor property, either x minus 2 is equal to 0 or e to the negative x is equal to 0. We just keep seeing this thing pop up in here, and it still has no solution. However, there is a solution here. That'll be at x is equal to positive 2. Now, given that that's a place where the concavity will be equal to 0. This will split up our real number line into two test intervals, which are from negative infinity to positive 2, and positive 2 to infinity. I'm going to try to do this one less wrong this time. I'm going to try x equals 0 for this one, x equals 4 for this one. I'll be plugging these into the second derivative. And the form of the second derivative that I'll be plugging it into will be this form right here. So we will get 0 minus 2 times e to the negative 0. That number is negative 2 times 1. That is less than 0. That means that on this interval, we are going to see that this thing is concave down. For the other interval, we'll test x equals 4. We'll plug 4 into, once again, this form. That'll be equal to 4 minus 2 times e to the negative 4 power. Simplified as much as possible, that'll be 2 over e raised to the 4th power. That number is positive. Meaning that on this interval, we are going to be concave up. So, interesting set of values that we're going to see for this. I'm going to take the intervals of increase and decrease, as well as the intervals of concavity, and put them together in the same spot so that we can sort of see what's going on. So important values that we got were 0 for an x-intercept, 1 for a local maximum, and 2 for our point of inflection. We'll do f prime on top, f double prime on the bottom. The intervals were increasing up until we hit x equals 1, at which point we will change to decreasing. For the concavity, we started out as concave down until we hit x equals 2. At x equals 2, it changed to concave up. We also had an x-intercept right at the origin, so I'm going to see if we can take all of these things and put them together. So first, we had our intercepts. Intercept was right at 0, 0. Then at x equals 1, something significant happened. At x equals 2, something significant happened. And we'll say that y equals 1 will be right up here. This is to emphasize the local maximum that we're going to have, just to give you an idea of the value that we're looking for the y value. 1 over e has a decimal approximation of just below 0.4, so in between 0.3 and 0.4. So that's going to be about a third or so, maybe a little bit higher. For our point of inflection, if we were to if I were to take x equals 2 and plug it into the original function, I would get 2 times e to the negative 2 power, or 2 over e squared. You can see that that's a little bit smaller than the y value that we had just gotten, so that'll be right about here. So all through this region, we're supposed to see something concave down, and as soon as we hit 2, it's supposed to be concave up, but still decreasing. We did mention earlier that there is a horizontal asymptote, and that horizontal asymptote is only on the right-hand side, and it'll be approaching y equals 0. We will see that behavior because it'll be decreasing and concave up. So putting all of this information together, I'm going to start at the local maximum here at 1, 1 over e. To the left of that, it's supposed to be increasing and concave down. Increasing and concave down looks kind of like this. So as we move to the left, it's going to be decreasing and then doing so more dramatically in that fashion. Still got the proper concavity though because the palm face is down. Then we'll be decreasing and concave down from point to point. Right at 2, we'll straighten out, and then we'll be decreasing and concave up as we slowly approach this asymptote. So this would be our complete graph of f of x is equal to x times e raised to the negative x.